techniques we're going through: substitution, usual substitution, and integration by parts, trigonometric integrals, and similar substitution but a slightly different direction. But for that we usually use this trigonometry substitution. And last time on Friday we actually learned to do about definite integrals, right? And exercises were about definite integrals. All right? Is everything all right? Now, last technique is PFD, partial fraction decomposition. So this it's one of the important technique that's used in differential equations. Wonderful course to take. So partial fraction decompositions are about polynomial functions, right? No square root, just polynomial functions. So there's this two important theorem about polynomial functions. All right, when it's not about partial fraction decomposition, whenever polynomials are introduced, this should be introduced. It's really a fundamental thing. Two theorem. Fundamental theorem of algebra, and after I introduce the fundamental theorem of algebra, there will be this unique factorization property. Two theorems about polynomials. Don't get confused. Two theorems about polynomials. There will be two theorems about partial fraction decomposition, right? But right now it's just about polynomials. Fundamental theorem of algebra is about polynomials. So here the polynomials. So first term I listed there is monic. Second thing is linear polynomial, quadratic polynomial, cubic polynomial. Those are about the degrees, right? Monic is not about the degree. And after that, we're going to introduce the notion of irreducible and reducible using this cubic example. Monic. Does anyone know what a monic polynomial is? This polynomial is not monic. X minus 2x squared plus 7, not monic. But following polynomial is monic. Is monic. Remember what a monic polynomial is? It is about leading coefficients. What is a leading coefficient? Right, leading coefficient of the first polynomial. What is it? Answer is not 1. What is a leading polynomial of a first polynomial right there? Leading coefficient of a first polynomial. Negative 2. Negative 2 is the coefficient of highest power. When it is expanded out like this, right? You can't easily read off the leading coefficient of, something like that, right? What is the leading coefficient? You probably have to expand it out, right? Or if I add x to the fifth, and it gets more, you have to expand all out, simplify, and then read that leading coefficient negative 2. If it is not 1, it's not monic. How about this one? What is the leading coefficient? It's 1, so we call it monic. So those polynomials are called monic polynomial. Okay? Make sense? All right. How about linear polynomial? Let me ask you this question. What is the degree of this polynomial? Any guess? No, it's the 7th. Multiply by 1 more. So exponentially, that's 8. And this 5, do we add 5 here or subtract or multiply? What do you do with that 5? Because it's below the degree 8. It's not going to affect, right? Degree 8. Does that make sense? Yeah. But if this is 8, and it might cancel off that coefficient, right? That are coming out. So you have to be careful. What is exactly the coefficient you get for x to the 8th? And that might cancel off to this x to the 8th, right? But if it's 5, the degree of this one is 8. So those linear, quadratic, cubic, refers to the degree of the polynomial, right? Linear is a degree 1, quadratic degree 2, cubic degree 3. Okay? So what is the degree of the following polynomial? They usually write it like this. Degree is official notation for degree of x minus 1, x plus 1, minus x squared. What is the degree of this polynomial? Because of the cancellation, x squared and x squared cancel. If you actually simplify it, it becomes, what does it become? Constant, actually, right? Is x squared minus 1 minus x squared. So it's a constant, right? X squared cancels. So what is the degree? Equal degree 0, right? Degree 0. Okay? So you actually have to simplify it and read off the degree. Cubic polynomial, degree 3, and so on. So that's the term. Irreducible, reducible. All right, it's about factoring, like numbers. X squared minus x minus 2 is called reducible. Can somebody tell me why this is called reducible? Since that quadratic polynomial is factored, right? Factored into linear, lower degree. So what are the factors? X minus 2, x plus 1, right? So lower degree here all over the real coefficients. Minus 2 is a real coefficient and plus 1 is a real coefficient, right? Not imaginary number, it's actual number. All right, so can you think of a quadratic polynomial that's irreducible? This one's reducible. How about this one? Do you think this one's irreducible? Irreducible or reducible? So if it is reducible, then it factors, right? Right, it doesn't nicely factors with the integer coefficient, but it's supposed to factor. So here, if it's reducible, it should factor like this, right? And alpha and beta are what kind of number? Real numbers. Not necessarily integers or rational coefficients. It could be irrational number, right? In this case, I think this is irrational numbers. So do you know how to find alpha and beta? Quadratic formula. Alpha and beta is a quadratic formula. If you keep this negative symbol and negative symbol here, if it's a positive, then negated answer from quadratic formula is the answer. So what is alpha here? 2 divided by plus 1, right? And plus minus root of b squared minus 4ac, I think that's 5, positive 5. So alpha could be one of these, and beta is the other. Does that make sense? So it factors like that. So degree 2 polynomial is written as a product of degree 1 and degree 1. Reducible, right? So what is irreducible? One, it's my favorite one. X squared plus x plus 1 is irreducible. It's not because we cannot factor. The fact that we cannot do it is not a proof of no one else can do it, right? And you have to argue it differently. So why is this irreducible? Because if it is reducible like this, right, then there must be alpha and beta. These are real numbers contributed to a real 0. But all the zeros of this polynomial x squared plus x plus 1 is imaginary numbers. Therefore, it's not irreducible. It's not reducible, excuse me. Since the root zeros of are all imaginary. Does that make sense? Okay. So here's one example. Let me write it like this: x plus squared minus x squared, like that, which is in more disguised form x to the fourth minus plus x squared plus 1. So this polynomial does not have real zero. All the zeros in this polynomial is imaginary. Is this polynomial reducible or irreducible? It's a trick question. So we concluded this polynomial is irreducible because all the zeros are imaginary, right? And I'm telling you, all the zeros, the 4 zeros, they're all imaginary. Do we conclude this polynomial is reducible or irreducible? It's actually reducible, right? This is not the reason that works for all the polynomial. That's the conclusion. It only works for quadratic polynomial. Okay? So how is this one reduced? Does anyone know how this one is reduced? This is the idea, a squared minus b squared. You see a squared minus b squared? How does that factor a squared? A plus b? A minus b, right? That's how it factors. Correct? This is a squared minus b squared. And it's a plus b and a minus b. But individually, they look like this, x squared plus 1, x squared minus x plus 1. And I claim both of them are irreducible because they don't have real roots, and it's because it's quadratic. Okay? This argument, zeros are all imaginary, only works for what kind of polynomial? Quadratic polynomial. Okay, that doesn't work for higher degree polynomial like this. Individual zeros of this one is imaginary. Therefore, all the zeros here is imaginary. But it's reduced. This degree 4 polynomial is reduced to, I think it's correct. Yeah, everything like that. Reduced to degree 2 prime times degree 2, right? So reducible, irreducible, this one. Reducible, right? All right, so don't abuse this argument. That's the notion of irreducible and reducible. All right? All cubic polynomials are reducible. Do you know how to explain this? All cubic polynomials are reducible. Why? I mean, there are infinitely many, all different shapes of cubic polynomial. How do you know this is going to be reducible? Right. Cubic polynomial is an odd degree polynomial. The shape of odd degree polynomial kind of like this. To the right, it goes to infinity. To the left, it goes negative infinity. Right? If you believe there's no hole in between, this connected thing will eventually cross this horizontal line, x-axis, introducing at least one real zero. Right? So this is called intermediate value theorem. You learn that in Calculus 1. Intermediate value theorem says if you want to go from one region to another region, have an infinite boundary, you must cross that boundary if you're moving continuously. It all makes sense when you're thinking about the physical situation and mathematical setting. This becomes very difficult to actually rigorously prove. So they named it intermediate value theorem. The point is that using the intermediate value theorem, there is one real root, right? Then it means it factors. So all the cubic polynomials factor into x minus alpha, right? Once it has linear factors, the other one is a quadratic factor like this. The point is that it reduced to degree 1 times degree 2. It's all reducible. It's due to what theorem? Intermediate value theorem. Because of intermediate value theorem, so what is the next example that we can argue easily? All the odd degree power, right? All odd degree polynomials are all reducible. The problem is even degree polynomial, right? So here's one example. It's even degree polynomial reduced to even. But in general, it becomes hard. And that is fundamental theorem of algebra. Okay? So here's the statement about the fundamental theorem of algebra. No matter what your polynomial is, they factor into product of linear, L1, Ln, they're all linear. X minus 1, x plus 1, x minus root 2, those are all linears. Maybe there is a multiple copies of x minus 1, so that's a multiplicity there. What are the Q's? Quadratic polynomial. One quadratic polynomial it's irreducible. Okay, these are irreducible. You can't factor any further because the zeros of a Q1 are all imaginary. Zeros of a Qm are all imaginary. You cannot factor any further. Maybe they appear as a multiple factors, your multiplicity there. You can always factor out all the leading coefficients and put it stack them outside and making all the other factors in here all monic. So here's a general statement. No matter what polynomial you have it there, px, they can be reduced to the following shape. All the powers of linear, all monic, all powers of irreducible quadratic factors like this, and plus some constant, which is the leading coefficient of a px, since everything else is a monic. It's always positive. There's no degree 3 or no degree 4 irreducible factor. They all reduce down to degree 1 or degree 2. Product of degree 1 and 2. That is called what theorem? Fundamental theorem of algebra. Sounds like important thing, right? It is a really important statement. All right. If I give you a quadratic polynomial, do you know how to quickly determine whether the polynomial is irreducible or not? There's some word called D word. Let's start with the D. So here's a polynomial, x squared minus x plus 1, and then you calculate something that is less than 0, and then you conclude, that's irreducible. Right, b squared minus 4ac. What is the name of that guy? Discriminant. So what is b here? Negative 1 squared minus 4 times a times c, which is 1. That altogether is negative 3, right? So that's a negative number. So it has imaginary roots for quadratic case. So you cannot factor any further. If you factor it, it contributes to 0. But if the degree is higher than 2, factoring does not mean that individual factors contribute to 0. That's why we couldn't use that argument for higher polynomial. All right? But if it's quadratic, that's the same thing. So that discriminant quickly tells you it's irreducible or not. All right? That's right. Yeah. Right. So here's another important thing down there is LK and QK are not necessarily computable, and I wrote that the existence theorem. What existence theorem do we know? Uniqueness of something, right? What's that? Antiderivative. That doesn't mean we can actually compute that antiderivative, right? You just know that, okay, it's out there, whether you can compute it or not. It exists in mathematical forms. It's the same thing. These polynomials, even mathematically, I can't compute it. But mathematical theorem asserts that it's out there. For example, I think I remember that example. And here, example of x cubed minus 3x plus 1. According to the fundamental theorem of algebra, how is it supposed to factor? Linear times irreducible quadratic, or linear times linear times linear, right? That's the only possibility, because the degree is 3. Degree 1, degree 1, degree 1, or degree 2 and degree 1, or this one it remained degree 3. Is this irreducible or not? It's reducible, right? But it turns out they actually have 3 real roots, real zeros. If you sketch it, it's right there. It crosses 3 times. Then you ask mathematics to compute what those alpha 1 and alpha 2 and alpha 3 are. Mathematics gives you disguised notation that uses imaginary. But if you really unfold that imaginary numbers, it really gives you nothing. My conclusion is that we don't have a notation for these alpha 1 and 2 and 3. No notation to properly describe this one using real radical without using imaginary. But it's right there. It crosses all the time. You can easily enter, we already did this example, like this one, it crosses real x's right there. If you ask Mathematica to compute it, we don't have a radical notation to write down the zero of this one. We have an approximate solution, always, truncated in 100 decimal places, but we don't have a notation for solution to this one. Actually, this one in here, like that. So that's what I mean by it's not actually computable. But there is real numbers that fill in this quadratic and coefficient of linear and quadratic in actually shaped like that. So understand the existence versus computable? Okay. The second one was unique factorization property. Now if you factors like this, and unique factorization property says there's no other way to do it. That's the only way. So like number 2015, I actually factored it. I never did it before. 2015 factored it into prime number 5, prime number 13, and prime number 31. And it actually there's no other way to do this. That's called unique factorization property. That holds for numbers as well. 2016, next year, is this prime factorization. And unique factorization is such that there's no other way than this one as a prime factors. This property is actually used to cryptography. If you have 3,000 digit prime number multiplied by another 3,000 digit prime number, and then it becomes a gigantic number, and this property tells you only way to factor that is knowing that two prime numbers. And actually searching for that prime number takes long time, connecting 10 supercomputers, something like that. So that's why we rely on that kind of thing in our financial transaction system, is completely rely on this unique factorization. Only way to do this is this. So if you don't know this one, you can't really factor it unless you just brute force search that takes. I heard that Pentagon crypto system usually takes 1 year to connecting tens of supercomputers. To searching for that prime factorization takes about 1 year. So they just replace it about 1 year with a new prime factorization, things like that. So it's mathematics behind that cryptography is relying on difficulty of this factorization because there's only one way to do it. So that's the thing about the polynomials, right? Two important theorems about polynomials. What are those? Properly educated, math-educated people should know this one, right? No matter what level they are, you should know the fundamental theorem of algebra about polynomials, and they factor uniquely, just like numbers, right? It's huge, hugely important. But our task is a partial fraction decomposition. So two theorems, remember? Two additional theorems coming in, and it's getting more complicated. I have to just introduce one and actually do examples and introduce the second one later. So this is actual business, partial fraction decomposition. Two important theorems for the polynomial to introduce. Now here, one of the two important theorems of partial fraction decomposition. I don't know, I think it came from KFC. This is incorrect. It's a PFD. It's supposed to be correct. There's a typo. So it's called Bazoo's identity. Bazoo's identity. Let's look at it here. There's two parts, existence and uniqueness. Denominator of this rational function, r is a polynomial, and p is a polynomial, and q is a polynomial. It seems like we're looking at denominator and factored into two pieces. All right? Okay, we have one polynomial divided by another polynomial. I factored one denominator into two pieces, p times q. And what is the condition about the p times q here? It's in colored red color, right? No common factor. Does that make sense? Like integer factorization, after you factor into irreducible, linear, and quadratic, there's no common factor between those p and q. Does that make sense? So for example, p being x minus 1, x squared minus x plus 1, x minus 2, versus q being x plus 1 squared x minus 2. Do you think they have two common factors? P and q, do they have a common factor? They do have a common factor, right? What are the common factors? X plus 1 and where's x plus 1? Is hidden inside there. If you factor, I didn't say it's irreducible, it's actually reducible, right? X minus 2 plus times x plus 1. So x plus 1, they're common factors. So this case has a common factor, right? Yes, go ahead. Thank you. So all the more reason to have some common factor, have a common factors. All right? So another example, here's x minus 2, and there's x minus 2. P being x minus 1, and Q being x squared minus x minus 2. How about that? Is that no common factor? Is that right? This one x minus 2, x plus 1, x minus 1. That's the irreducible factor, so this one has no common factor. Okay, no common factor. So situations like this, to see that, you actually have to factor, right, completely to irreducibles and, check one by one, okay, there's no common factor. But what is the key? You have to factor into irreducible. Don't leave it like x squared minus x minus 2. Factor completely, right? Now, if so, then they can rewrite this r divided by pq as r1 divided by p plus r2 divided by q. They can always do that. And it's unique if they don't have a common factor. That's what I meant. Right? It's possible to write it like this. And if they don't have a common factor, there's only one way to do it. There's no two answers for R1 and R2. There's a unique answer to that. So it's possible to split it. This is called partial fraction decomposition. Another statement is it's actually unique. This is not very important for our calculation, but it's something that has to be mentioned. Unique when this r is less than the numerator has degree less than the denominator. Okay? If the degree is greater than, it's not unique. You can, confuse those decomposition. All right? So if you want to integrate r divided by pq, if you can split it like this, it turns out integrating r1 divided by p, r2 divided by q is slightly easier. That's the whole application to that. Right? If you're looking at this function in here, difficult to integrate, you can split it. Now individual terms you can integrate. All right? So here is an application on. Yeah, I think, why don't you hide that and make this one of the first exercise today. Don't look at the statement and see if you can separate your statement. Existence part in here, and what is the uniqueness part of this Bezoos identity really stating. That's your first exercise. Try to recall what we just saw that. Okay, what is the existence of a Bezoos identity? What is the uniqueness of a Bezoos identity? So I have this much about existence. R divided by PQ equals R1 divided by P, R2 divided by Q. And who remembers the condition in here? It's about P and Q, right? Have no common factors. No, there's additional condition on that to ensure the uniqueness. If this is true, then we have existence. If there's no common factors. But if there's additional conditions there, then is R1 and R2 is unique. There's no other R1 and R2 that makes these two things equal. Yeah. So let's do that. Uniqueness of what? What is unique? This R1 and R2, right? P and Q and R that's given in the problem, this R1 and R2 is filling in these equations, and there's no other choice for R1 and R2. And what's uniqueness is guaranteed when does it happen? It's about the degree. Degree of R is less than the degree of denominator P times Q. Okay? Then there's only one way to do it. Okay? So we use this existence, and rely on that one and figure out what R1 and R2 is. So here's an example. Well, I think I wrote here. This Bezoos identity, which has two-part existence and uniqueness, there's an algorithm there. This algorithm is not necessarily convenient to ensure there's existence and uniqueness. So we don't try to learn the algorithm of Bezoos identity, which is out there. You can look for it. But what we're going to learn is probably much better than efficient than this Bezoos identity. But our algorithm relies on the existence, right, of the Bezoos coming from the Bezoos identity. So for that, we introduce two techniques. The first one is a very standard, everybody talks about this one, method of comparing coefficients. And this guy works all the time. And the second one is like three different things you're juggling here and there according to the situation. And often this is really fast. This is slow, works all the time. The first line works all the time, but often slow. Second one, method of specialization and reduction, really fast, but sometimes it doesn't work. So I wrote here, method of comparing coefficients works all the time, but a little bit slow. Second one is juggling these three things, reducing the numerator and specializing, and sometimes you have to differentiate if there's multiple factors like the multiplicity R1 and they're involved. So a lot of juggling back and forth, but small example, this guy worked really fast. All right? So I know it's impossible to, I'm just listing it and you're just looking at it. I'm not expecting that you remember any of this at the moment, but you should remember two things about polynomials. What are those? Fundamental theorem of algebra and uniqueness property. And what about the first of the two things about partial fraction decomposition? Bezoos identity, right? So here's an example. Do you see that it's in that form, R divided by P times Q already, right? But often they don't factor it like that. You have to factor it, right? So kind of polish your skill on factoring degree 3 polynomials, right? Here's a degree 3 polynomial, expanded. How are you going to factor this, right? Think about that. But if it is factored like this, do you agree these two things have no common factors? First of all, are those all irreducible? That's one thing you can check, you have to do before you check your factors. Is x plus 1 irreducible? It's irreducible. You can't reduce any further. Degree 1 is the bottom, right? How about x squared plus 1? Irreducible because the zeros are I and negative I, or discriminant is negative 4. So is irreducible. So this is irreducible factor, monic. Irreducible factor. They don't have common, right? So our theorem applies. Okay, let's do that. Here's an example. First one is a method that works all the time, comparing the coefficients. But let me first show you the structure. What does the Bezoos identity tell you? If it is like this, it's right, R1 plus R2, and what is in here? X plus 1, and what's in here? X squared plus 1, right? These two things are always the same. And also, this degree of 1 here, what is the degree of a polynomial 1? Degree 0, right? Also, what about here? The degree 3, right? So it has a uniqueness, right? And I think I forgot to mention that this degree of R1, let me write it here. I'm going to fix that. R1 is less than the degree of x plus 1, the numerator. Additional condition in here. Degree of R2 is less than the degree of x squared plus 1. That's a part of the Bezoos identity, I forgot to mention. Not only it factors like this, it factors such that the numerator degree is always smaller than the denominator degree. You keep this condition right here, degree smaller than the degree of the denominator, and even in decomposition we keep that same. So if a polynomial R1 has a degree less than the degree of x plus 1, what is degree of x plus 1? So 1, degree 1, x to the first, linear. So what is the degree of R1? 0, right? That's what you're thinking. So what is the degree of polynomial that's degree 0? It's constant. So any linear, you will put constant up there. Okay? That's the convention. So that's going to be like an A in there. How about R2? This is a degree 2, right? Quadratic, irreducible. So below here is degree at most 1 or 0, right? So what kind of polynomial is degree 1? Linear polynomial. So that looks like bx plus c. So Bezout's identity guarantees that 1 divided by x plus 1, x squared plus 1, is decomposed into the following set. A constant a, x plus 1, plus constant b divided by x squared plus 1. Not b, it's a bx plus c. That's what Bezout's identity guarantees. Okay? It doesn't, the way it's stated, it doesn't tell you what a and b and c are, but it is in that shape. That's all it says. Now we're going to use this method of comparing coefficient to figure out what this a and b and c are. Does that make sense? This is really brute force, comparison. So here, because of these denominators split like this, this is always least common multiple of a denominator. So you multiply the denominator. I'm going to call that one d. Excuse me. If I multiply d both sides, you see left-hand side becomes just 1 because d cancel. Okay. If you multiply it here, x plus 1 times d is x plus 1, x squared plus 1. That's multiplied there. And bx plus c, x squared plus 1. And also we multiplied x plus 1, x squared plus 1. I multiplied the denominator, so it canceled the original denominator on the left-hand side. Right-hand side guaranteed by, in that shape, by Bezout's identity, and you multiply the denominator there. See this x plus 1 cancels? Right? And this x squared plus 1 cancels here, right? So what does that become? This constant polynomial 1 in the left-hand side is always identically equal to a times x squared plus 1 plus bx plus c, x plus c. Bezout's identity says that this is always true, not just for special values of x. Always true. Make sense? Yeah. So if you expand the right-hand side, things cancel out, just leaving 1. That's what it means. Right. So I'm going to continue going. There's 1. Remember what I said about this method of comparing coefficient? Works all the time, but it's lengthy and takes a long time. That's what this one is. All right. Can you collect the coefficient of x squared? I want you to look at this expression and multiply it out in your head. And think about collect everything that has x squared in it. Do you see a in it there? A times x squared. Do you see that? Okay. So there's one more term that has x squared in it. What do you say? B. Yeah. B times x squared. Bx times x, that's bx squared. I hope you see that there's no other x squared term. That's it. So here's a challenge. What about x? Do you see x? Do you see x here coming out from x here? I don't see any x coming out here, right? How about here? Yeah, b and c, b plus c. Okay, let's collect the constant term. What constant term do you see? A. Here's a times 1, so a. There's one more term, c. So if you collect all that, whatever that A, B, C are, they somewhat cancel out, leaving only one. So if they cancel out, what should be happening to that A and B there? They should be opposite sign. No matter what, they just cancel, become the coefficient 0, right? And they become a 0. And what about this one? They cancel, or should be 1. Why is that 1? Because that has to match the left-hand side. If the left-hand side is not 1, but x plus 1, then this should be 1, so that 1 times x plus 1 matches, and this one 0. So I'm looking at left-hand side as a 0 times x squared plus 0 times x plus 1, and comparing the coefficient of a polynomial like that, concluding the first coefficient 0, second coefficient 0, and third coefficient 1. So this gives us what kind of equation? A plus b is 0, b plus c being 0, and a plus c being 1. This is called linear system of linear equation. So if you can solve this equation, and that's the answer. The question is, in general, if it's like this, if it's all the other different situation, guaranteeing that this 3x3 system of equation is always solvable or not, that's another question that it's not easy to answer. This is a specific question. We'll try to solve it, and if it's solvable, very good, we have a solution. But in general, is this always solvable? Which goes back to the existence of question. Bourdieu's identity says there is always ABC, right? So it exists. So that question is really linked to the existence we rely on to know that. So the solvability of this equation is guaranteed by Bourdieu's identity. All you have to do is to solve. Do you know how to solve this system? You eliminate one variable at a time. So let's eliminate, for example, a here. You see, if I multiply negative in here added there, do you see that becomes negative b? A cancels, and plus c, and the negative is a 0. You see that? And that's, I obtained this one. I'm going to call that one number 1, number 2, and number 3. I got this one by negative 1 plus number 3. Negative a, negative b is equal to 0. I added it here. The negative a, positive a cancels. So negative b plus 0 plus c equals 1. So I got this new equation about b and c and b and c. So now we're looking at 2 and this equation 4, if I label it. 2 and 4 is about b plus c equals 0, negative b plus c equals 1. So that's 2 by 2 equation. Usually you know how to solve this one, right? So how do you get rid of b? Add 2 and 4, is that right? Then you get rid of this b, so we end up at 2c equals 1. So what is c? 1/2. Then if this is 1/2, what is b? By looking at this equation, must be negative 1/2, right? Negative 1/2. So I got b and c. By looking at this equation, if b is negative 1/2, what is a? Positive 1/2. Okay? This one is a really easy one, but you will see the nasty one. It takes quite some time to actually solve completely. This 3 by 3, and at worst it goes to 5 by 5. 5 by 5 eventually. So that second technique is really precious, that you don't have to solve 5 by 5 in some cases. All right, so here is the answer to that one. 1 divided by x plus 1, x squared plus 1 is equal to a. What's a here? 1/2, right? 1/2 x plus 1 and x squared plus 1 here. What is b? Negative 1/2 x plus c. That's a positive 1/2. That's the decomposition. All right? So they usually pull out then 1/2 as well. So here's a 2, x plus 1. Let me pull out negative 1/2 there. Then x minus 1. Do you see that? Because I pull out negative, that has to be x minus 1. And down there, x squared plus 1. So this is a decomposition. Something is decomposed into individual parts, And I hope you find that this one is something you can integrate individually. Do you think you can integrate the first term? What function kick in as you integrate this one? ln, right? ln kick in. What about this one? You have to split the fraction, right? With the first one, first split, what technique does it apply? U substitution, right? X squared plus 1 being u. What about the second split? Negative arc10, right? Arc10. So that's how this one works. If you're asked to integrate this one, you go through this massive business and split it, integrate individually. All right? So here's what you've long been waiting for. So that one is this command. 1 divided by x plus 1. So please check your answer with this one, okay? After you do that. So it did that for us. If you ask a pot and it decomposes for us. Right? That's something like we just did, right? Yeah. All right. Then you can integrate it. Does that make sense? All right. That's example 1. And that is method of what we just did is the method of comparing the coefficients after you multiply the denominator. All right? This works all the time. So I'm going to ask you to practice decomposing pod tonight.